The next set of problems we're going to work on are a set of acceleration problems, and the first one that was assigned is number 17. Number 17 states that a Dr. John Paul Stapp, the U.S. Air Force, who studied the effects of extreme deceleration on the human body. On December 10, 1954, Stapp rode a rocket sled accelerating from rest to a top speed of 282 meters per second, 1,015 kilometers per hour in 5 seconds, and was brought to a jarringly back to rest in only 1.40 seconds. Calculate A, his acceleration, B, his deceleration, and express each in multiples of g, 9.8 meters per second, by taking the ratio of the acceleration to gravity. Okay, so the first part of this problem is the acceleration part of this problem from a v0 of 0 to a v final, and it's assumed, because it says this, that this is a uniform acceleration of 282 meters per second. And so A, the acceleration, is going to equal 282 minus 0, v final minus v initial. And the time it took for this to happen was 5.00 seconds. And so the answer is going to be positive, right to left or left to right, 56.4 meters per second squared. And it's positive because we're saying that left to right motion is positive. So acceleration is a positive motion. Now, the second half, the v initial, is the 282 meters per second, and the final is 0, because that means that it's stopping. And so the acceleration here is going to be 0 minus 282 divided by, and this occurs in only 1.40 seconds. If you do the math here, you get 200 minus 201 meters per second squared, which means the vector of acceleration is now right to left instead of left to right. Now, expressing these in g, all you do is take the 56.4 and divide that by 9.8, and the 201 divided by 9.8. And this will give you 5.76 g. And this one is 20 minus 20.6 g. So that's the first problem, first acceleration problem. The second one, constant acceleration in one dimension. An Olympic sprinter starts a race with an acceleration. Now, this time they're going to tell you what the acceleration is. So they start the race with a constant acceleration of 4.50 meters per second squared. At what speed does she reach after 2.4 seconds? And this is assuming that she is accelerating at a constant rate. So we know that V0 is 0, and that VF is what you want to know. And we know that A is equal to VF minus V0 over T. So AT, and since Z is going to equal VF, which is going to equal 4.50 times, and the time was 2.40 seconds, and so you end up with a final velocity of 10.8 meters per second. And the second part of this was to graph this, and it says assuming the acceleration is constant, we know that x is equal to 1/2 at squared is equal to well, the question was, sketch the graph of her position versus time during this period. And what you would do, and can't, is you would have time on this axis and position on this axis, and you know that here's time and here's position, or the x coordinate, and you know that d is equal to v0t plus 1/2 at squared, and v0 is 0, so d is going to equal to 1/2 times 4.5 times t squared. And so for a t is 0, you're going to be 0. At t is 1, 1 squared is 2, or 1 squared is 1 times 4.5 times 1/2 is 2.25. 2 is going to be 9. And if this is 1 second, 2 seconds, 3 seconds, 4 seconds like this, you start here, and this is, say, 5, 10, 15. And so you start 0, then at 1 you're at 2.25, which is about right there. At 2 you're up to 9. And so your curve is going to look something like that. And so you should probably try to do a little better of a graph job than I've done here, but this is, if you go ahead and do 3 is 20.25, so it's going to be up about right there. So let me straighten this out just a little bit, do a little bit better job here. I'm not a great drawer, but something like that. And so, and it keeps going like that. And if you have constant acceleration, your velocity is increasing, which is why this is curved upward like this when you're looking at the position. Number 22 states, a bullet in a gun accelerates from the firing chamber to the end of the barrel at an average velocity, or an average acceleration, of 6.2 times 10 to the 5th meters per second squared. So the acceleration is 6.20 times 10 to the 5th meters per second squared. And the time is 8.10 times 10 to the minus 4. 8.10 times 10 to the minus 4 seconds. That's how long it takes it to reach the end of the barrel. And the question is, what is the muzzle velocity, or the velocity as it exits the barrel? This is actually quite easy. There's two ways to do this, but probably the easiest is to use the equation that VF is equal to V0 plus AT. V0 is 0, so VF is going to equal AT, which is going to equal 6.20 times 10 to the 5th times 8.10 times 10 to the minus 4, which is going to equal 502 meters per second. I wrote 3, but it's 502 meters per second. The next problem, acceleration, again, another acceleration problem, is problem number 26. And number 26 states, blood is accelerated from rest to 30 centimeters per second in a distance of 1.8 centimeters in the left ventricle. A, make a sketch of the situation. Okay, so if we're going to make a sketch of the situation, basically you start at 0, and we'll just pretend that's the bottom of the left ventricle. And here is the exit from the left ventricle over here. And so here's the x distance that's covered during that time. At time 0, this is at time 0, x0 here is going to be 0. We're going to define this as the starting point. V0 the blood's not moving when it starts, it's equal to 0. And so the question is, what is the acceleration? The second question, over here we don't know the time when it reaches the end, but we do know that x1 is equal to 1.80 centimeters. We do know that at that point, VF is going to be 30 centimeters per second. And we don't know here what the acceleration is either. So at these 2 points, this is what we know and don't know. So the first question, so that's the drawing picture. Then the next step is to, once you sketch it, is to write down the knowns, which I've done here. So part B is to write down all this known information. And then part C is to find out, answer the question, how long does it take the blood to accelerate? And then it says to solve this blah, 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 which you can go ahead and do that. So T, so the question is, what is T? We know that it goes from x zero to x over a period of time, and this is based on the average velocity. And the average velocity is going to equal, and so we know that x minus x0 is 1.80 centimeters, and we know the average velocity is the final velocity minus the initial velocity divided by 2. And so the final velocity is 30 and the initial velocity is 0, so that's 15. 30 divided by 2 or 15. So we end up with 1.8 centimeters divided by 15 centimeters per second. And if you do the math here, you get 0.120 seconds. And then D states, does the answer seem reasonable to compared to the time for a heartbeat? Now, at first blush, you would say no, because it seems like if you took this as the entire cardiac cycle, you're talking about a heart rate of somewhere in the range of 500. But the real cardiac cycle, D, the real cardiac cycle is about a second. But that includes both systole, which is when this occurs, and diastole. And so immediately that 1 second is divided by 2 because this is not happening during diastole. And so now you're down to 1.05 seconds. And then the actual time of contraction is a fraction of this. And so this number seems like it could be a reasonable number. Let me do one more problem, number 32. And number 32 states that a woodpecker's brain is especially protected from large decelerations by tendon-like attachments inside the skull. While picking on a tree, the woodpecker's head comes to a stop from an initial velocity. So the initial velocity is 0.600 meters per second. Not squared, just meters per second. And the final velocity is 0. This can be I or 0. Let's use the same all over. And so it goes from 0.6 meters per second to 0 in the distance of 2 millimeters. So D is going to be 2 millimeters. Now, since this is in meters per second, it might be nice to change this to meters per second. So that's going to be, or to meters. So that's going to be 2 times 10 to the minus 3 meters. A millimeter is 1,000th of a meter. And so the question is, find the acceleration in meters per second and in multiples of g. Just taking these numbers right here. And we know that VF squared is equal to V0 squared minus 2x minus x0 a, okay? And that's one of the formulas in your book, and that's the formula that should make it onto your card, by the way. And so if you rearrange this, you end up with A is equal to V squared, Vf squared minus V0 squared divided by 2 over x minus x0. And if you put the numbers in, Vf is 0, so you end up with a minus 0.6 squared over 2 times 2 times 10 to the minus 3. And so the deceleration here is minus 90 meters per second squared. And if you divide that by 9.8, you get about 9.18 G. Then B says that because of these ligaments, well, first of all, it asks you to calculate the stopping time. So x minus x0 is equal to 1/2 times v0 minus vt. And so if you do that, this is the average velocity. V0 minus v is the average velocity and the time here. And then if you move this over there, then the time, you can calculate the time because that's going to be 2 millimeter, or 2.0 times 10 to the minus 3 meters divided by 2, because of the 1/2 here, divided by 0.600. And so the time for this deceleration is going to be 6.67 times 10 to the minus 3 seconds. So that's a lot of G's pretty fast. Now, the point here is, though, that with these tendons, the stopping distance is changed from 2 millimeters to 4.5 millimeters. And so recalculating the G-force based on this change in stopping distance, we use the same formula we had up here, but and we put in the same numbers, 0.6 squared divided by, but now it's going to be divided by 2 times 4.5 times 10 to the minus 3, because that's the changing in the stopping distance, because the tendons allow it to move forward and then move back, and that's going to make it a minus 40 meters per second squared, 40.0 meters per second squared. And the G here is now goes from 9 to 4.08 G. So it more than halves the G-force on the brain. And so that's, and when I read this, I remembered the movie Concussion, which was a very interesting movie where they talked about the G-forces on the brain and how animals that have these kinds of G-forces have protective structures. And that's exactly what this problem shows you, is that there are protective structures in the brain for animals, but not for humans.